and Dr. Prem, Dr. Akhilesh, and greetings to all of you. I mean, it's after congruent numbers, maybe it's time to see the generalizations of it. Okay. May I talk about just overview of our understanding about rational triangles, and I'll briefly mention our work with Professor Saikia and my advisor Dr. Diophantine Chakravarti and Shamik Das.
From there, so Krishna, go once more. No, I think once more. Keyboard. No keyboard. Then keyboard. Try once. And then keyboard.
Okay, so outline of my talk will be like I'll introduce what are Heron triangles.
See, echo is there.
Fine. Okay. I'll introduce what are Heron triangles and recall some results about congruent numbers and some progress about it and its connection with elliptic curves, what just Professor Saikia mentioned. Now, and I'll talk about relation between Heron triangles and Diophantine equations. And then I'll talk about a family of elliptic curves from Heron triangles and its bound, which is our recent work. And then I'll put up some questions about it, and then I'll give list of references. Okay, so triangle with rational sides and rational area, so what we call rational triangles or Heron triangles. So why we call them Heron triangle is Heron from the Greek. I mean, he was a Greek. Heron, of Alexandria, Greek mathematician. He was the first. Who made the connection between the number which can occur as area of rational triangle and the sides of the triangle. Okay, that relation was established by him. So we call, in his book Metrica. So that's why in his honor we call them Heron triangles. So that formula is square root of an S minus A, S minus B, and S minus C, where S stands for the semi-perimeter of the triangle. Okay. So he did this relation in the 1st century, but most of the things we don't know about rational triangles. And I need this formula in the 21st century. So what we are motivated the following questions. So given some angle theta, can a natural number occur as area of rational triangle? Okay. So in the literature, this is the generalization of congruent number problem, where we assume theta to be 90 degrees. So this was definition of congruent number. It is occurring as like an area of rational triangle, right angle triangle. Okay, and it was equivalent to the Diophantine equations: x square plus y square z square and xy by 2 is equal to n. Okay, I want to just point to this observation because we want to generalize this, the relation between these triangles and Diophantine equations. Okay, for example, 5, 6, 7, these are the congruent numbers, but n was not a congruent number. Fermat's legacy, because he introduced the method of infinite descent. But it can occur as area of some other rational triangle. Right? Rather, given any n, there is some rational triangle. For that. Okay, so regarding this congruent number, like we can look at them as using the Diophantine equation for right angle triangles. If that numbers can occur as area of right angle triangle if and only if, there are these 3 numbers, u square minus n, u square and u square plus 1. These all are squares of rational numbers. There are 3 terms in the arithmetic progression with difference n. Okay. And using this fact, we arrive at equation with some substitution, which looks like y square is equal to x cube minus n square x, and which is as elliptic curve. That's what we have seen just in the Shaikia's talk. Okay, an elliptic curve. What we were saying yesterday also, I mean, Rene mentioned how we can reduce elliptic curves with short West transform for not characteristic 2 and 3 and group law on it. Okay, so for natural number, I mean like square free integers, there is a one-one correspondence between these Diophantine equations and the points on the elliptic curve. So on the left-hand side, we have because Diophantine equations, and on the right-hand side, we have points of infinite order on elliptic curve. Okay, so I believe this is an elegance to see the connection between them. And this is a model theorem. Model theorem is a rational points on elliptic curve. They form finitely generated abelian group. And as we have seen, so now congruent problem reduces to the finding the rank of that elliptic curve. If that rank is positive, then we say that number, corresponding number, where y square is equal to x minus n, x plus n for that number n. Okay. That number is congruent number. And in this regard, breakthrough was made by Tunnel, as he said. He reduced to the some finite algorithm, finite steps. Like he introduced these sets A and B and C and D and Diophantine equations. And when A is equal to n by 2, if it's happening for odd numbers, and Cn is equal to Dn by 2 for even numbers. And but this converse part is dependent on PSD conjecture. So which means we do not have description for all congruent numbers yet. For example, n is equal to 1. So for an and bn's, we have only y is equal to right, plus minus 1. Only two solutions, but they don't satisfy this criteria of Tunnel. So we can say yeah, 1 is not a congruent number. Okay, again in this regard, I mean, Higner's work. I mean, Higner was interested in congruent numbers, and for 5 mod 8 primes, I mean, he showed that existence of points of infinite order. And but his work was realized later by Birch. Okay, and he found that this method can be used for other and to construct the rational points on elliptic curve, rather on large class, not only just congruent elliptic curves, but modular elliptic curves. Okay. And Jan recently generalized it for highly composite number. Okay, right now I'm just reading this work. Like I wouldn't say reading, mostly I'm struggling to understand most of this Jan's work, but okay, so reading this history of progress of our congruent numbers. Okay. Now I would like to just take this result about now generalization of this congruent numbers. What Goins and Maddox did, now existence of this rational triangle with some area n is equivalent to this generalized elliptic curve. Okay, y square is equal to x into x minus n tau into x plus n tau inverse, where the tau is a rational number tan theta by 2 has point of infinite order on this elliptic curve, which is not a point order, then we can say such a rational triangle exists. So that given, and we call them as Heronian elliptic curve. Okay. So as I said, this is a generalization because if we choose tau is equal to 1, then it will reduce to the congruent elliptic curve. Okay. So this is also, and we have this explicit transformation from triangle to curve and curve to triangle. Suppose we have triangle with, then we can have point of infinite order from there with this given formula. And once we have this point of infinite order on the elliptic curve with given curve what I mentioned here, then now once we have point of infinite order, we'll get the sides with this transformation, right? We'll get the side A, B, C. Okay. And so now keep on doubling it or add to the torsion points. We will get again the corresponding A, B, C different. Okay. For all those points, we will get, but area will be same, that number n. Okay, so once we get the point of infinite order, we'll get the infinite triangles with the same area. Okay. Now I'll talk about this Diophantine equation. The Indian astronomer Brahmagupta in the 7th century, he showed the necessary and sufficient condition for when can integer numbers occur at sides of the triangle. Then there should be this number should be in proportion. There is an ABC, then gave this some property, necessary and sufficient condition. He mentioned these results in his book Brahmasputa Siddhanta. Okay, but modern proofs can be seen in the Carmichael's work. Okay, so using this information, what we did is for 5 modulo 8, okay, for this class, and where p square plus 1 is equal to 2q, then this corresponding elliptic curve is having rank 0. It means there are no rational triangles with areas with this kind of p, and angle one of them is 1 by p. And wherever now when p is 3 or 7 mod 8, then the bound of the triangle is at most 1. Okay, so whenever this rank is 1, there will exist infinitely many triangles. Okay, and moreover, for every odd prime p, so what we are saying is there is a 1-1 correspondence between the solubility of this Diophantine equation and the existence of rational triangle with area p, and tan theta by 2 is 1 by p. Okay, so this is kind of generalization of Pythagoras theorem for this family. These are a few examples using magma. I verified it. Okay, and now I'm going to recall some results on what are studies going on rational triangles. Okay, Buchel is very much interested in this rational triangles, and he is looking into this rational triangles with 2 rational medians, because this is again one more long-standing conjecture. Can we have a rational triangle with all 3 medians rationals? Okay, such triangles, some author call it as perfect rational triangle. Whether such triangle exists or not, they are looking into it. And Ghale, I mean, who is I think one of the speakers tomorrow, I mean, he also worked on this triangles. He found out some ranks 9, 10 bounds, I mean, on these Heron triangles. Okay, and then Elizabeth also showed some existence of curve at least 2. Okay, the point I was making is in the study of congruent numbers, it was important to study the Selmer groups, like Professor Saiki also mentioned recently. Hip Brown, they studied the Selmer groups, Selmer 2, Selmer ranks of congruent elliptic curves. But in the case of rational triangle, it is missing. So at least for some family, we tried. I mean, to bear, we assume that the area is 2 to the power m, and one of the, I mean, tau, what I was mentioned previously, was 2 to the power m. Then this 2 Selmer rank of that elliptic curve is 1 when m is 1, and otherwise it is 2 Selmer rank is between 1 and 3. Okay, and again, what Mahesh was mentioning this, assuming finiteness of Shah group.
So just I think say your PQ is equal to 1. Probably you have something.
Sure.
EBA prime convert to 7 mod and Q prime such that PQ is equal to 1. I think maybe you need to there's something else.
Maybe listen.
Sorry, yeah. So, thank you. Yeah. Okay. And assuming this Shah group, so we got that rank flow we want. Okay, and some distribution of these ranks. I mean, you got using again magma and sage. Okay, what I mean, Kenor also mentioning using just we can get the ranks and Selmer ranks. Of course, you must be knowing, but in case if you don't know the commands for using magma and sage, so you can find it here. Personal. Okay, some questions. I mean, what we are doing for triangles? The question is, I mean, can we do it for other polygons also? Right? Because if you're having some integer sides or rational sides, all that, can we relate those numbers which can occur as areas and all the polygonal numbers which are integers and rational, right? And again, we can connect it to the elliptic curves and Diophantine equations. And to say about congruent numbers over various number field. Now people, mathematicians are working on this. I think Shakya sir also worked on this in real number fields. And as we have Pythagoras theorem and what we work for other families, so can we have for each of the Heron triangle corresponding Diophantine equation? And like what Tunnel did, like for 90-degree, theta is 90-degree. So we should, can we have the same criteria, simplifying to the some Diophantine equation for other Heronian elliptic curves? And again, for like Higner's idea, also can we construct for other Heronian elliptic curves? And again, like Selmer proposed theoretically, it's computable. But as I've seen in our work also, for some elliptic curve, we are not able to get using magma and sage. So, I personally like to play with this using magma and sage and see some patterns of the ranks. So, can we have some better algorithms for computers to compute this Selmer rank? And these are some references. Puja's work can be seen in Heron triangles with 3 rational medians. And this Selmer, and seeing the Selmer group of for that family can be seen in the construction of infinite family curves, and the connection of this rational triangles and Diophantine equation can be seen in the article Heron triangle and a Diophantine equation. And this idea of generalization from congruent to other rational triangles can be seen in Heron triangles via elliptic curves and Selmer groups, Shah groups, and this method we are using to count ranks of that is descent method that can be seen in Silverman, and this Igner's idea and this generalization can be seen in Tian's work. That's it from my side. Thank you. Thank you.
Questions for